Good day, class. You're welcome to my YouTube channel once again. I'm Adeyeye Adelu Peter. Today, we want to look at density and upthrust. So, what is density? The density of a substance can be defined as the mass per unit volume of that substance. Density of a substance equals mass over the volume of that substance. And it is measured, the unit, that's the unit, it is measured in gram per cm cube or kilogram per meter cube. Gram per cm cube when the mass is measured in grams and the volume is measured in cm cube. Then kilogram per meter cube if the mass is measured in kilogram and the volume is measured in meter cube. So these are the two units we use for the density of a substance. And the density of every substance differs depending on the nature of that substance. For example, the density of water is not the same thing with the density of kerosene. It's not the same thing with the density of paraffin. It's not the same thing with the density of gold, and so on and so forth. The density of water, please don't forget, we use rho equals mass over volume. We use rho, this Greek letter to represent the density of a substance, rho. So the density of water, as I was saying, density of water, H2O, is 1.0 grams per cm cube or 1,000 kilograms per meter cube. That's the density of water. Density of kerosene, although it varies depending on the content of the kerosene, you can have 0.8 gram per cm cube. Density of ice, 0.9 gram per cm cube. Density of mercury is 13.6 gram per cm cube, and so on and so forth. So you can see that the density of a substance depends on the nature of that substance. And the density also tells us how heavy a substance can be. For example, since the density of water is lower than that of mercury, so we can say that water is going to be lighter than mercury. Or we say the same volume of water will be lighter than that of kerosene. Equal volume of water and equal volume of mercury, not kerosene, of mercury cannot have the same weight. Mercury is going to weigh more than that of water because the density of kerosene is more than that of water. All right. Now, how do we measure the density of a substance? How do we measure the density of a substance? Measurement of the density of, let me first look at a regularly shaped object or solid. So how do you measure the density of a regularly shaped object? For example, a cubical steel, a cuboid made of steel or made of iron, whatever. So how do you find the density? So if it is a cube, this is a cube. So a cube is regularly shaped, all right? So the length is going to be L, length L. So how do you measure the density of a regularly shaped object like a cube, a steel, a cubical steel, all right? Now what you do, procedure one, is to measure the dimensions That's the size, the dimensions of the object. And for this one, what do we need? We need the length. That's the length of one side of the cube, and the length is L. That's the first thing we are going to do. Now, why are we measuring the dimension? Density is equal to mass over volume. So we are measuring the dimension in order to get the volume of that particular object. So after measuring the dimension, you now find the volume. You use the formula volume of a cube for the one that is a cube. Cube equals L cube. So that's the volume. Then the next thing is to weigh the object. Why are we weighing the object? We are weighing the object using a weighing balance. This an electronic balance. So we can use this one to weigh. So you set it to 0. Then you place the object on top in order to get the weight. All right. So when we weigh the object, we get the mass. Say mass m in grams. Then the next thing is to calculate the density. What is density? Density is equal to mass over volume. So density will be equal to, what's the mass? M over L cube. All right. So that's for a regularly shaped object. Now, what about an irregularly shaped object? Irregularly shaped object like that of a stone. Irregularly shaped object like that of a stone. You can see this. This is a stone. So, and it is irregularly shaped. So I'm going to change this to measurement of density of an irregularly shaped object, e.g. stone. All right. Now this time around, the first step is to measure, we are going to measure the volume. Now, you know the reason why we are measuring volume? We cannot measure the dimensions. We cannot calculate the volume. We can only measure. Since we cannot get the dimensions of this stone, nothing like length, nothing like breadth, nothing like height. So the best is to measure. And what is the procedure for measuring the volume of an irregularly shaped object? There are two things we can do. Is either we use a measuring cylinder. The measuring cylinder is graduated. Use a measuring cylinder. Now, assuming this measuring cylinder is filled with water. This is a measuring cylinder. It contains water up to this level. Let me assume this level is 10 cm cube. All right? 10 cm cube. That is when the stone has not been introduced. 10 cm cube. But the moment the stone is introduced, what happens is that the volume rises above 10 cm cube, right? Here is 10. So let me assume here is 15 cm cube. When the stone has been introduced, this is stone. Because the stone will help us to increase the volume of water that is inside. Now, the volume of water has risen by what? By what amount? Rise in volume of water. Rise in volume of water is going to be 15 minus 10, which is 5 cm cube. Therefore, the volume of stone is what now? 5 cm cube. All right? Volume of stone is 5 cm cube. So we use a measuring cylinder. to achieve that. That's one way of measuring volume of an irregularly shaped object. What is the other way? The other way is using an Eureka can. An Eureka can. This is how an Eureka can is shaped. This is how an Eureka can is shaped. We have something like this. There's an opening here. So you fill water to this level of this opening. Then what's the next thing to do? You can introduce your stone. You can see, if you introduce the stone will make the water to overflow. And when it overflows, it begins to come out of here. The water will come out of here and it will start to drop here. So whatever the volume you're able to gather here, whatever the volume, maybe 5 cm cube, that's going to be the volume of the stone that is immersed here. So that is how we use the Eureka can to calculate, to measure the volume of an irregularly shaped object. Then afterwards, you can now use formula. Sorry, before you use formula, you also measure the mass of the stone using this. Measure the mass of the stone using electronic balance. This electronic balance comes in different sizes. I think this is the smallest size, right? So after you get the mass, you now do density equals mass over volume, which will now be equal to the mass you measured over the volume you also measured. All right? Now, what about the relative density of a substance? I'm going to treat relative density halfway here today. Then, in my subsequent videos, there's a reason why I will not treat everything here. If I treat everything here, you may not understand the way you are supposed to. Relative density. Relative density. Relative density. Now, what is the relative density of a substance? The relative density of a substance is the density of that substance as compared to that of water. Or we can say it is how heavy a substance is when compared to water. So it means water is the standard substance which we use to compare the density of other substances. So relative density, RD of a substance is equal to density of the substance divided by the density of water. And it happens that it has no unit. The reason why it has no unit is because it is a ratio. It is a ratio. All right? We still have many other formulas. We have many other formulas for relative density. So it has no unit. And please, I want to give you a note, a very important note. Note that the relative density of any substance is equal to the density of that substance in gram per cm cube. Now, whenever what I'm trying to say is that whenever you know the density of a substance in gram per cm cube, just remove the unit. That value you have is the relative density of that substance, because relative density has no unit. All right. For example, the density of water is equal to 1.0 grams per cm cube. Now, what do you think the relative density of water is going to be? It means the relative density of water will now be 1.0. What did I do? Just copy the value, the magnitude you have there, 1.0. Then what do? Remove the units. The density of kerosene equals 800 kilogram per meter cube. Find the relative density. There's a reason why I'm doing this. Now, we already know the density of kerosene in kilogram per meter cube. What I'm trying to say is, once you know the density of a substance, either in gram per cm cube or kilogram per meter cube, you already know the relative density. This time around, we are given the density of kerosene in kilogram per meter cube. So what do you think you are going to do? Convert that density from kilogram per meter cube to gram per cm cube, and then you remove the unit. So the value you have is going to be the relative density of kerosene. So density of kerosene is 800 kilogram per meter cube, which is the same as 800 divided by 1000. I know you may be surprised we are dividing by 1000 to get the unit in gram per cm cube. You can work it through yourself. I have no time for that. So if I divide, what I have is 0.8 gram per cm cube. But what are we asked to find? The relative density. Now, since we've gotten the density in gram per cm cube, relative density of kerosene will now be equal to 0.8. Just remove the unit behind. So that is the relative density of kerosene. All right. Now, I said there are other formulas for relative density. There are other formulas for relative density. Relative density of a liquid is mass of the liquid over mass of equal volume of water. Or you say weight of the liquid over weight of equal volume of water. You know the difference between mass and weight? Mass is measured in grams, while weight is measured in kilogram. We still have some other formulas, but when we get to Upthrust, we are going to iron that out. All right? Now, there's something I want to point our attention to again, and that is Upthrust. Upthrust. I believe we all know that thrust is a force. It's a force. Force of what? Of push. Thrust. Then when we now say up thrust, it means the push is now upward. the push is upward. So what it means is that upthrust is a force, all right? And is an upward force. Is a force which a fluid exerts on any object that is placed in it. And when we talk about a fluid is anything at all that can flow. Anything that can flow. Either gases or liquid. So example of gases, we have air. So air is an example of a fluid. Liquid, we have water, we have petrol, we have paraffin, and so on and so forth. So these are examples of fluid. So when we talk about upthrust, is an upward force which a fluid exerts on any object placed in it. And it is measured in what? In Newton, since force is measured in Newton. All right. So upthrust is going to be measured in Newton. All right. Now, this takes us to Archimedes' principle. Archimedes' principle. Archimedes' principle. Now, what does Archimedes' principle say? It says that when a body is totally or partially immersed in a fluid, it experiences an upthrust which is equal to the weight of the fluid displaced. That's Archimedes' principle. When a body or when an object is totally or partially immersed in a fluid, it experiences an upthrust which is equal to the weight of the fluid displaced. Now, what is Archimedes trying to say? If you have been in the countryside before, which in Africa we call village, you must have drawn water from the well before. If this is a well and this is the bucket of water, this is a rope with which you draw. All right. This is the water in the well. Now, the bucket has water inside also. All right. Now, you will discover that as far as the body of the bucket is still inside the water in the well, and you are drawing with a force upward, it will be very easy for you to draw. Now, the reason why it's very easy is because upthrust is exerted on the bucket by the water. The water in the well is exerting an upward force on the bucket, helping you to push. You are pulling upward. Upthrust from water is also helping you to push. Although the weight of the bucket is acting downward, the weight of the bucket is acting vertically downward. But what happens is the moment the bucket gets out of the water, now this is the bucket. The moment it gets out of the water, you now begin to feel the weight of the bucket Upthrust has withdrawn. No more upthrust. Upthrust becomes 0 here, but here we have upthrust. All right? So that is what Archimedes is trying to say. Now, it happens that the upthrust that this weight of bucket and the content is going to fill in water can't be the same thing it will fill in kerosene. It can't be the same it will fill in mercury. Now, what I'm trying to say is that upthrust depends on the fluid itself, the nature of the fluid. And when I talk about nature, I'm talking about the density of the fluid. For example, if you have different container, one with kerosene, one with water, and one with mercury, and you have to drop a cube of steel inside. Now, the cube of steel will go down the most inside kerosene and the least inside mercury. This water, you can see that a bigger part of it is outside. Now, this is mercury, the same size, you can see. So, what I'm trying to say is that upthrust in each of these is not the same thing. Upthrust in kerosene is the least, while upthrust in mercury is the highest. Mercury will exert the highest force, the highest upward force on this steel than both water and kerosene. The kerosene will exert the least force because the density of kerosene is the least, while the density of mercury is the highest. Now, we have a formula for upthrust. We have a formula for upthrust. And what's the formula? Upthrust on an object equals to density of the fluid upthrust on an object equals density of what? Of the fluid in which the object is placed times volume of object, then times G. Now, we are going to use G. No, G is measured in meter per second square. This formula is applicable when density is measured in what? In kilogram per meter cube, and then volume is measured in meter cube. I know there's a formula that you guys are not familiar with. I'll give you another formula. Upthrust on an object equals density again of fluid times volume of object, then times 0.01. This time around, it is when the density of the fluid is in gram per cm cube, volume is in cm cube. So that we are now going to use 0.01. And I think I should show you how I arrive at this formula. Now, I want to show you something. But before that, this upthrust depends on what? Density of fluid and the volume of object. According to this, it says when an object is totally or partially immersed in a fluid, it experiences an upthrust, which is equal to the weight of the fluid displaced. So before I go further here, I want to talk more on this formula. But before I go further, please, I want to give a question. Now, according to this formula, to this principle, what Archimedes principle is trying to say is that upthrust, please let this one sink down. Upthrust is equal to the weight, that's upthrust on objects is equal to weight of fluid displaced by the object. You can write this formula down. This formula. Now, you can jot this one down, please. Upthrust on an object is equal to the weight of fluid displaced by the object. Let me show you what we mean by that. Let me give you an example. A stone was thrown inside a bucket of water, displacing 0.2 Newton of water. What is the upthrust on the stone? Okay. A stone was thrown inside a bucket of water, displacing 0.2 Newton of water. What is the upthrust on the stone? Solution. I know some of us will be calculating. Maybe they even give us density of water. Density of water is 1,000 kilogram per meter cube. Now, this one is just a distraction. That density is a distraction. At times, they may even give us the mass of the stone. Let me add to it. The mass of stone is equal to, let me say 3 kg. Now, I want you to know that all these are distractions. So from here, let us go back to the definition of upthrust. Upthrust on object, that's when an object is in a fluid, either partially or totally submerged. That upthrust is equal to the weight of fluid displaced by the object. Let me show you what I mean by that. At least I showed you something the other time. What's this? This is water. This 10 cm cube. Now imagine you now throw a stone inside. The water level is going to go up, maybe to 15 cm cube. Now the volume of water displaced, is 15 minus 10, which is 5 cm cube. That's the volume of water displaced by that stone. But for you to calculate the upthrust, you have to convert this volume to what? To weight. But this time around, they gave us the weight directly. So what's the answer? Upthrust here on stone is going to be equal to 0.2 Newton. Now, what if the question is like this? The answer is 0.2. What if the question is like this? A stone was thrown inside a bucket of water, displacing 3 cm cube of water. What is the upthrust? what is the upthrust on this stone? So how do we go about this? Now, solution. This time around, you will see that what we are given is the volume displaced, not the weight. Upthrust must be in weight. That's in what? Newton. Upthrust must be in Newton. But this one around we are given the volume of water displaced, not the weight. So volume of water displaced is 3 cm cube. Now watch. So how do you now get the upthrust? Convert this volume of water displaced to what? To weight. If you can get the weight of water displaced, it means we have to know the weight of this water. Since this is the volume of water displaced, we get the weight of water displaced. And how do we do that? We use density equals mass over volume. Even if you are not given the density of water, you should know that one offhand. Please. So what's the density of water? You must use gram per cm cube because the volume given to us is cm cube. So that's 1.0. Then mass over volume, which is 3. So what's the mass? Mass is going to be equal to 3 times 1, which is 3.0 grams. But what are we asked to find? The upthrust. And what is upthrust? Weight of water displaced. Now we just got the mass of the water displaced. What do you do next? You convert to weight. What is weight? W equals mg, which is now equal to, what's the mass? 3. Now, this mass is in what? Is in gram. So just to convert to weight now. Sorry, this mass is in gram. So we have to convert to kilogram. So mass in kilogram, that's going to be what? 0.003 kg. That's 1, 2, 3. So it means our weight now is going to be mg 0.003 times 10, and that's 0.03 Newton. So that's the upthrust. Now, if you study this formula very well, you will notice something. If you study this formula very well, you notice something. Let me show you something here. There was a formula I gave to us the other time on upthrust. So let me show us. From here, what do? We made mass the subject of formula. Now watch. Mass is equal to density times what? Times volume. Now, density of what? Density of what did we use? Density of water. The fluid in which the object is placed. Then volume of what did we use? You will notice that this volume of water is the same thing as the volume of object immersed. Volume of object of what? Object immersed. Do you remember that when we were trying to calculate the volume of an irregularly shaped object, we dip the object completely inside a measuring cylinder or inside an Eureka can. And the volume displaced is exactly the volume of what? Of object. So despite the fact that this is the volume of water displaced, it's also equal to the volume of object that is inside. So this volume of what? Of object. All right? This is what we did there. Then mass is density times volume. Now when we converted the mass to what? Kg, and then multiply by 10. Definitely it means this is what? Upthrust. This times G. You first converted to, so if this is our mass in kg, then what do we do? Because density times volume is mass. Then convert this one to what? That's convert this one to Newton now by multiplying by 10. It means this mass has turned to upthrust. So that's why we got that formula. Upthrust is equal to density of fluid times volume of object times G, or density, depending on the unit, gram per cm cube times volume in cm cube, then times 0.01. All right. Now, there's another thing I want to iron out here. There's another thing I want to iron out here. You know, a spring balance can be used to get the weight of an object. A spring balance is an instrument that can be used to get the weight or the mass of an object. Spring balance comes graduated in mass, in grams, and in Newton. Some, they write the mass in grams and the weight in Newton side by side. All right? Now, imagine you have a spring balance. This is spring balance. This is a spring here. And then a weight is hanging. This is a weight. And let me assume that the pointer is now pointing that this weight is 20 grams. Or let me say 0.2 Newton. Now, this weight is hanging freely in air. The weight of any object hanging on a spring balance freely in air is the original weight of that substance. That's the actual weight of that substance. If I'm to be hanging freely on a spring balance, whatever I weigh is my weight. For example, I weigh 75, so if I'm to be suspended on the spring balance, I'm going to be weighing 75 kg, mass anyway, mass, not weight. If you want to convert it to Newton, you have to multiply by 10, that's 750, all right? So this is the weight of this object in what? In air, which is the actual weight of the object. Now, if this spring balance with this weight hanging on it, if the weight is now suspended in water, let me suspend it completely in water. What do you think the reading is going to be? With a rigid support here, the reading is going to change. And how? This water is going to exert an upthrust force. That's upthrust on the weight. And what happens? The weight is going to reduce maybe to 0.17. This is the pointer now. The weight is going to reduce. Now, the new reading, this weight in what? In water. Weight in water. So that the new reading of the spring balance is equal to what now? 0.17 Newton. Less than 0.2 Newton when the thing was in air. So who can tell me? What is the upthrust experience? Because this one has experience and upthrust. So it means upthrust experience now is equal to what? The weight in air minus weight in water, or reading in water. Reading in air minus reading in water. What's the weight in air? The original weight, 0.2, minus weight in water, 0.17. So that's 0.2 minus 0.17. And that's 0.03 Newton. So water exerted an upthrust of 0.03 Newton on this object. So making the weight to reduce from 0.2 to 0.17. All right. So from here, I can now move further by giving more definitions on the relative density of both solid and liquid. So I move further. I'm going to move further to give us an idea on relative density of a solid and of a liquid. So relative density again, RD of a solid. So there's another method that we can use to determine the relative density of a solid. Relative density of a solid now is equal to the weight. Now, what do? You weigh the solid in air, then you dip it in water and weigh. The weight is going to reduce. So of a solid is equal to the weight of solid in air over upthrust in water. Please, we are not using just any fluid. We are using water. We are using water. So assuming the weight in air is W1, which is this. This is W1, and the weight in water is W2. So it means the relative density of that solid. What's the weight in air now? W1. Then what's the upthrust? That's the loss in weight. Loss in weight in water. W1 minus W2. So that's another formula for relative density of a solid. All right. Now, hope you guys know that we can also use the same procedure to get the relative density of a liquid. Okay, let me show us. This is the last thing we are going to do in this session. This is the last thing we are going to do. Relative density of a liquid. Now the next thing I'm going to introduce here, please, this W2, don't forget. The next thing I'm going to introduce here, this same procedure, my spring balance. I'm going to introduce a liquid of unknown relative density. This is water. This liquid L, unknown. Okay? Now, definitely the upthrust exerted by this liquid cannot be the same with that of what? Water. There's going to be an upthrust exerted by this liquid. So the new weight, now let me assume that the new weight here in this liquid is 0.16. It must be less than weight in air. It must be less than. So I'm going to call this W3. I want to determine the relative density of this liquid. So relative density of liquid, this time around, you can see that even the solid is involved. The solid is involved in determining the relative density of a liquid. So we know the weight of the solid in air. We immerse it in what? In water. We get the weight. We also immerse the same solid in a liquid of unknown density. We get the what? The weight. So what's that relative density of liquid? That's going to be upthrust of the solid in liquid, upthrust of solid in liquid over upthrust of the same solid in water. And what's the upthrust in liquid. Original weight in air, the weight of the solid in air minus the weight of the solid in liquid. Loss in weight. Don't forget that upthrust is lost in weight. Then what is the upthrust in water? So that of water is always going to be down. W1. Sorry, this W3. W1 minus W now. What 2 now, right? So W1 minus W3 over W1 minus W2. So this is part 1 of 3, because I'm going to be dropping 3 videos on this topic. This is just part 1. So part 2 is going to be calculations on density, calculations on upthrust. But before I round off, I think I forgot something again. I forgot something. Sorry for that. Very important. Very important. What I just forgot is this. At times, they may mix 2 substances together. 2 liquids may be mixed together, and even 2 solids may be mixed together in the case of alloys of metals. And you'll be asked to calculate the relative density of one of them, or even of both, or whatever, or volume or mass of any of them in the mixture. So density of mixture, density of mixtures. If 2 substances A and B are mixed together, it can be kerosene and water, it can be zinc and copper. All right? It can be zinc and tin mixed together. Let the mass of A be Ma and that of B be Mb. Now, if the volume of A is Va and that of B is Vb, also given that the density of A and B are respectively rho A and rho B. Now I want to point our attention to something here. Density of mixture, very important. I wonder how I forgot that. Now, can we get the total mass of the mixture? Yes. What's going to be the total mass of the mixture? Mass of the mixture is going to be mass of what? Of A plus mass of B. That is Ma plus Mb. You'll be very correct. For example, if the mass of A is 10 grams and the mass of B is 15 grams, definitely the mass of the mixture, if you mix it together, if there's water here and there's kerosene here, and I'm to weigh them, if this one weighs 15 and this one weighs 10, if I mix them together, the mass of the mixture, the kerosene and water together, is going to be 10 plus 15, and that's 25 grams. All right? So we can add masses together. What of volume? Volume of the mixture can also be added to get the total volume of, the volume of individual can also be added to get the total volume of the mixture. will be volume of A plus volume of B. What is not volume I used the other time? Mass 15 gram, 10 gram, 25 gram. Now, if it is volume, let me say 30 and 20. If you add it together, if this one is 30 cm cube and this one is 20 cm cube, total volume is going to be 30 plus 20, and that's what? 50 cm cube. All right, very correct. You can't be wrong with that. But if we want to find the density now of the mixture, that is where most students get it wrong. You don't add the density of each of the individual components to get the density of the mixture. You'll be wrong there. So density of mixture is not equal to density of A. It's not equal to density of what? Of B. So let's assume it's water and kerosene. Water is 1.0 gram per cm cube. Kerosene is 0.8 gram per cm cube. So can you now add it together and say the density of the mixture will now be 1.8? That is not possible. You know, the density of mixture depends on how much of water and how much of kerosene we have. For example, if you have 10 grams of water and 2 grams of kerosene, the density is going to be more than when you have 2 grams of water and 10 grams of kerosene. So the density of this one is what? Is higher. While the density of this mixture, this particular mixture, is what? Is low. So please, if you don't add density, so water has a higher density than kerosene. So if you mix more of water than that of kerosene, the density of the mixture is going to be more than when you mix more of kerosene than that of what? With that of water, I mean. All right? So how do you now get the density of the mixture? Density of the mixture is going from the formula density is equal to mass over volume. So what's the total mass of the mixture? So mass of the mixture, MA plus MB, over volume of the mixture, VA plus VB. That's how you get the density of the mixture. All right? So my next video, I'm going to be dropping calculations, and please, it may be long, it may be as long as this, in order to buttress my point. Thank you. You can like, comment, share, and please don't forget to subscribe. Thank you.